Okay, let's see. Picking it up again. So I think after the last couple of days, which have been sort of on the more advanced side, we're going to take a step back here. So, I mean, after studying all these sort of geometry theorems and whatnot, I mean, to really sort of start to get toward real proofs of these things, one doesn't really do geometry, one does analysis. It's really, I mean, they're kind of the same thing. So the idea is that in the end, the geometric picture of your space, I mean, the type of structure that exists on it, is going to be more or less the same, once you figure out how to say it right, as finding what kind of functions have what kind of properties on your space. So we kind of had this discussion very briefly at the very beginning when we were discussing, say, the Bakary-Imry estimates and whatnot. But now we'll sort of, it'd be nice if over the next 2 days we can start to see some sort of estimates for elliptic and parabolic equations that exist on spaces with lower Ricci bounds that don't have to. In particular, today we'll focus on two things. So we're going to focus on Harnack, so actually differential Harnack and Harnack, inequalities, and estimates on the heat kernel, and Gaussian estimates in the heat kernel. So the point is we know perfectly well that in Euclidean space that the heat kernel is a Gaussian function exactly. And the idea is that on a typical space with lower Ricci bounds, it actually does at least have, from above and below, Gaussian bounds. It does look like a Gaussian function. It is, on a Riemannian manifold, the right replacement for a Gaussian function in many ways. And we'll sort of estimate this more directly today. But where we're going to start right now is in just sort of stating and proving the Liao differential Harnack inequalities. And I'm just going to state this and prove this for non-negative Ricci. There's no difference in the proof, and the main thing about the statement is that it's the statement's almost the same for a typical lower bound. There's definitely a statement, but I couldn't find it on Google, and I don't remember quite what it is. So people don't tend to write it so well. So that means I'm just going to state it for non-negative Ricci. Essentially, you're going to add a k to everything, and it's going to be the lower Ricci version. But I mean, one has to be careful about exactly how you write it. So anyway, the theorem here is the following. So this is going back to Liao, and this is what you call a differential Harnack inequality. So let's let M and G be a complete space as usual with Ricci non-negative. And let U sub t be H sub t u bigger than or equal to 0, be a non-negative solution of the heat equation. And the following holds. Ugh. Then we have the inequality with the gradient of the log of ut squared minus the time derivative, so dt or dd, that's right, it's ddt of log ut. Well, we have that this is less than or equal to n over 2t. This is extremely important. We're going to use this to prove, so this is what you call the differential Harnack inequality, and we'll use this to prove the Harnack inequality. So roughly, this will basically just say that if we look at the heat kernel in some neighborhood of space-time, the value can't change very much, or any positive solution of the heat equation for that matter. The solution can't change very much in space-time. And I mean this kind of in a sort of in a ratio sense as opposed to just a bounded sense. So this is where our Gaussian estimates will eventually come from. Okay, so how do you prove such a thing? So the proof is basically just sort of a sequence of computing equations for things and applying maximum principles. You got to find the right equations to sort of compute, and you got to find the right ways of trying to actually bound them. But let's just do this in steps. So claim 1. Well, since this is an equation depending on just log u, it makes sense that we should understand. I mean, whenever you're trying to bound some sort of function of something that itself solves an equation, you kind of want to know what equation does that solve. So that is to say, if we let f, or f sub t if we want, be equal to log ut, just so I can give it a name and not write log every time. Then we have that ddt of ft is equal to the Laplacian of f. So it's not going to be a solution of the heat flow anymore, but it's going to be pretty close, plus the gradient of f squared. So you can interpret it in this two ways. Well, one way is sort of a nonlinear heat equation. The other way of saying is that it solves the heat, the f sub t heat flow, if you kind of want, but it doesn't matter. So let's just go ahead and see if this is true. This is a simple enough computation. Proof. Well, ddt of f is just equal to ddt of log u. That's just equal to, so I'll use ddt or u dot, depending on what's sort of more convenient. So that's just equal to u dot over u. U dot over u is equal to the Laplacian of u over u. So now we want to rewrite this in terms of the Laplacian of ft. So with this computed, the next natural thing to do is compute the Laplacian of ft. Well, the Laplacian of ft is itself. So if this is one computation, and now we're going to move to the next computation so we can try to figure out what this is in terms of f. Laplacian of f, what is this? This is di of log u, which is equal to di of diu over u. And now we have two terms from this. The first one hits the top, and the second one hits the bottom. So this is going to be equal to the Laplacian of ut over ut. Well, that's actually extremely convenient because that's exactly what's appearing here. And the second term is minus the gradient of ut squared over ut squared. Okay, but then if we plug that just simply back into here, what's that mean? That means that ddt of ft, which we already showed was equal to the Laplacian of ut over t, that's now equal to the Laplacian of ft. But now we need to get rid of this term on this side, so we got to move that to the other side, so it becomes plus the gradient of ut squared over ut squared. Okay, but what is that? That's just exactly the Laplacian of ft plus the gradient of ft squared. So this proves the first claim. So, I mean, I'm going to say something, and this is probably not going to mean a lot unless you've done this computation an awful lot. But nonetheless, I'm going to say it once so that at some point in your sort of future when you're doing a lot of these computations yourself, at some point it'll sort of pop in your head and click. So very similar computation here would have been to compute not the rate of change of the log of u, but the rate of change of u squared, say. At which point you would have gotten very much the same thing here. It would have been a Laplacian, but the big difference is that there would have been a minus the gradient of u squared here. And this is a big difference when you're actually doing your maximum principles in your computations. Somehow the log is going to make the sign point in a different direction. and that this is sort of key to why certain things work. But whatever. Okay, fine. So we've seen that the log actually obeys some nice equation. But now this is not what we're actually trying to estimate, right? Well, we're trying, and if you see what we're trying to estimate. What we're trying to estimate is that top term there, and depending on the gradient of log u squared. So instead now what we're going to do is let's look at that term. So this is a slightly more involved computation, but it's still just a computation. So let's let f, capital F sub t. Well, let's let this be equal to t times the gradient of f squared minus f dot, which by our last computation is exactly equal to minus t times the Laplacian of ft. So, definition. Then it's really this guy that we're trying to control, right? What we're really trying to say when we phrase it is we're trying to say this is always bounded from above by n over 2. That's really what the Liao-Harnack inequality is. That this guy has an upper bound. So that means that what we really want to understand is what's the equation this guy satisfies. We're going to want to apply a maximum principle to this thing in the end. So the claim here, so here's our definition. Then ddt of ft. So in this case, we're not going to get an exact equality. I mean, we could, but it wouldn't be nice in capital F. We want something just in capital F. But we will get an inequality, which is good enough for our purposes. So this is less than or equal to 2 times the gradient of little f and product the gradient of big F plus 1 over t times big F minus 2 over nt times big F squared. I feel like I'm maybe missing a Laplacian term. It's not written in my notes, but I'm pretty sure there's a Laplacian term, so I'm just going to stick it there and we're going to find out. Okay, so why might this be useful? So let's just point out why this is a useful equation before we prove it. If our goal here is to prove that this function here is always less than or equal to n over 2, then what do you do for maximum principles? You try to pick a point where maybe it attains a maximum, and you see what happens to the rate of change of your function at this point. This is the spirit of it, right? So if we pick a point where this is a maximum, then what happens? Well, the gradient of it vanishes. It's 0. So you always get to throw away gradient terms when you're doing maximum principles. The Laplacian of it is less than or equal to 0, so it at least has the right sign. So you get to throw this term away, too, at a maximum point. Now, what's left is this. And if you're at a point where, where you're at your maximum point and it's already less than or equal to n over 2, then this is also less than or equal to 0. So the point is that if we're at a maximum point and that maximum is less than or equal to n over 2 itself, then the rate of change is less than or equal to 0. This is I mean, you've got to be a little finessing to actually make this, make it into a rigorous statement, but this is the moral of how a maximum principle works, right? So it's a useful equation. I mean, we'll do that more slowly. I was just throwing it out there for now. For now, let's just compute the equation and see what we have it. So proof. So let's start with a couple of computations that are just useful at this point. So let's look at the Laplacian of the gradient of f squared. So we know exactly what this is. We've actually done this computation about 5 times, at least the first line of it. That is, it's just a Botner formula. I mean, for any nice smooth function, this is just equal to 2 times the gradient of the Laplacian of ft times the gradient of f t plus 2 times the Hessian of ft squared plus 2 times the Ricci of gradient of ft, gradient of ft. So Ricci hasn't actually appeared yet, so it's good it appears somewhere. So what can we say about this term? So let's first do just a couple of silly things. I mean, first off, this first term here, well, the Laplacian of ft is precisely equal to minus 1 over t capital F. Right? I mean, that's what we have up here. So this first term here is actually exactly just equal, so no equality from here. This is going to come from dropping the Ricci term. 2 over t times the gradient of ft, gradient of little f. So that's nice because this was by far the ugliest of the terms, so this is now gone. Note that the truth of this statement came down to this last computation we did up here, right? So I mean, that's really where that played a role, was that we could have two different ways of writing what capital F was. Let's just keep this term for the moment, and we'll talk about it next. And this term here, well, we'll throw it away because we have non-negative Ricci. Yes. So we're looking at the Laplacian of f, yes? So all I've done is replace the Laplacian f by capital F over minus 2t, right? So those are the new terms here. And our capital F was this guy, but by our last computation, that was equal to minus t Laplacian of f. So all I did was take this Laplacian of f term, move this minus t over to this side, and plug it in. Okay. Now, we'd like to do something with this term as well. Now, we've done this trick before, and we'll do it again. This is an extremely important, not only is this important, this is in some sense, again, I'm throwing out something that won't have a feel for you for a while, but I kind of want to use the words. This is where dimension plays a role. Dimension appears in this inequality here, right? I mean, being non-negative Ricci is not all that's going on. And a lot of the statements we've made, somehow they were really dimension-free in a sense. This is not dimension-free. This is an estimate that depends on dimension, and it's going to be right here, in fact. And the reason for this is that, remember, if you have any n by n matrix, we do it up here. So if M is an n by n matrix, then we have this sort of standard inequality that says that the norm of M squared, oh, that's this guy, is always going to be bigger than or equal to 1 over the dimension, n, times the trace of M squared. I think I assigned this as homework last time, but I'm going to assign it as homework again. It's a nice computation to do. I mean, it's very, very simple. I mean, just sort of subtract and add on the trace here and see what happens. Right? You'll get that this is equal to this plus something else which is non-negative. But we want to apply it here. So when we apply it here, we get this is bigger or equal to minus 2 over t. Gradient of little ft, gradient of big F, plus 2 over the dimension times the Laplacian of f t squared. So our Hessian becomes a trace, becomes a Laplacian. And finally, I just want to play this game one more time because we want everything to be in terms of big F in the end. Our Laplacian of f, once again, it's capital F over minus t. We don't care about the minus because we square. And this is precisely equal to minus 2 over t. Gradient of little f, gradient of big F, plus 2 over n t squared, capital F squared. Okay, so what? So now to compute our inequality, so just, well, heck, let's just do it one term at a time. Let's be slow about it. That's fine. Whatever. So we want to compute what the heat operator applied to capital Ft is. This is the real goal. So we sort of have to pick which point of view we want to take for capital Ft. For ddt, I want to take the point of view of this being minus t times the Laplacian of ft, because this just becomes minus the Laplacian of ft, which now just becomes ft over t. Oops, I forgot a term, didn't I? I cheated. So I have to hit two terms, right? When I ddt this thing, I hit the t term, but I got to hit this term too. So the first term is this, and the second term is minus t times the Laplacian of f sub t dot. That's better. And I'm going to leave this term alone for now because I have foresight of what's going to happen in the next computation. And we'll replace this guy by capital F. Similarly, we want to compute what minus the Laplacian of capital Ft is. I'm doing minus the Laplacian, not the Laplacian, so I can just add these two terms and see what happens, as opposed to having to subtract them. It makes no difference. It's just more convenient. So in this case, what do? I'm going to take the first point of view of Ft being t times the gradient of f squared minus f dot. And what we get is that this is equal to t times minus the Laplacian of the gradient of f squared. Luckily, we've done this computation, plus the Laplacian of f dot. So in particular, when I look at the sum of the two, so if I look at ddt minus the Laplacian of ft, so this is what I really care about, then when I add these two up, this cancels this, and what's left is ft over t minus t times the Laplacian of the gradient of ft squared. Okay, but we went to all the trouble of figuring out that this guy is bigger or equal to this guy, which means minus it is less than or equal to. So let's keep the first term over t. We get our minus. Well, if we let our minus t just flow through here, we get plus 2 gradient of ft, gradient of big Ft, and then minus 2 over n t times f sub t squared. And if I'm not wrong, that's exactly what we were trying to compute. And that was exactly what we're trying to compute. Great. Okay, so fine. We've done two really long computations at this point. So let's finish the proof of the Liao-Harnack, Liao differential Harnack. Because it makes life easier, I'm going to assume our underlying manifold's compact. Completely unnecessary, but it lets you stop from doing it. I mean, this is sort of the typical thing you have to do. If you try to do maximum principles on non-compact spaces, you always got to be a little careful and make an extra argument to actually take care of the fact that there may not be a maximum point at some point. It doesn't matter, but you got to argue it, and I don't feel like it, so we're going to assume compactness. Just so we can get the idea across. Okay, so what are we going to do? So let's actually let G epsilon, or maybe I'll stick it up here. Let's let G epsilon t be equal to f sub t minus epsilon t. This is a typical trick you do for maximum principles. You want to be a little careful about a certain inequality that appears at some point. We want to show that the maximum, which we're going to actually denote by something, an epsilon of t, which is defined to be the maximum of G epsilon t. This is over all x. Is less than or equal to n over 2. We want to show this for all epsilon. So if we can show this for all epsilon, then it holds, if just letting epsilon goes to 0, it holds for f, right? Okay, so how do we actually do this? So now the idea is that let's note one thing real quick. G epsilon of 0 of x. I mean, this is just equal to f0 of x. And our definition here precisely guarantees that this is, identically 0. Because we multiplied it by t. So for sure, I mean, this holds at t equals 0, and by some continuity or whatever in a small neighborhood of 0, say. So let's, before I throw that one, I'll say is what we're going to show is that ddt of m epsilon of t is strictly less than 0. I'll write it over there. I don't want to squish it. Okay, so what we're going to show if m epsilon of t is less than or equal to n over 2, then ddt of m epsilon of t is strictly less than 0. In other words, we're done, because we're initially 0, and if at any point our maximum got up to n over 2, it would have to decrease right away. So it couldn't have gone above n over 2. So automatically, so let's call this star. So star implies that m epsilon of t is always less than or equal to n over 2, which implies that m0 of t, since this is for all epsilon, is less than or equal to n over 2, which implies that our f sub t is less than or equal to n over 2, since this is just the maximum of this. So we'll be done at this point. So this is the main goal. Okay, so how do we do this? So this is the more of a maximum principle. So what we say is that, so let's look at some t. So let's let xt be such that our g epsilon of t of xt is equal to our maximum. So this was just the maximum of g epsilon sub t. So remember, that's just f minus epsilon t, nothing fancy. So this should be just sort of a standard argument at this point, but we'll go ahead and write it out. So then what do you do? So what you want to understand is, so what's ddt of gt epsilon at xt? Well, remember, this is just the same thing as ddt of f sub t at xt minus epsilon t. And what's this equal to? Well, this is equal to a whole bunch of things involving capital F, but I mean, they all involve gradients of capital F, which means that whenever we have a gradient of capital F, we can replace that with a gradient of capital G, because we're just minusing a constant off in time. I mean, this is a function that's constant in space, right? So this is actually equal to the Laplacian of g epsilon t plus all the rest of this nonsense. What is this? So, less than or equal to. Plus 2 gradient of ft, gradient of gt, plus, oops, maybe I lied about that. Let's see what happens. Plus 1 over t gt. And then if I minus the epsilon, I get add epsilon. Can't say I'm a fan of that. Minus 2 over nt. Probably should have written this out before I came in. Of gt plus epsilon t squared. And then we get to minus from all this epsilon t. That's not good.
Should there be a t there? I think when you take the derivative with respect to t, just become...
You're saying, no.
The first line, it should be minus epsilon, not minus epsilon t.
Thank you. That's at least better. Okay, so that's minus epsilon. Now what about the rest of these terms? So this is equal to Laplacian of gt epsilon. So cancel, cancel. That's not exactly what I was looking for, but we'll just let that go. Plus 2 times the gradient of ft. I'm concerned I had to be a little bit more clever than just minusing epsilon t off this, but we're going to find out. Minus 2 over nt, g sub t squared. And then we have plus 2 times this. So this is minus 4 over nt epsilon. T's go away. G sub t. That's not so bad. Okay, hey, this is not so bad. Okay, great. Minus 2 over n times t times epsilon squared. Okay, so I'm going to throw that in. So the maximum is bigger than or equal to 0, but less than or equal to n over 2, then the rate of change is negative. And that doesn't matter, because if it's less, if it's strictly less than 0, then certainly our maximum is less than n over 2, and we're happy anyway. We don't really care. All the rest of the implications are the same. So now what happens when we look at this? So now let's play with this equation. So now the point is we're evaluating all of this at a maximum point, right? So the fact that we're at a maximum point means that the first term is less than or equal to 0. The Laplacian of something at its maximum is always less than or equal to 0. It's a maximum point, which means the second term is 0. The gradient of this function vanishes. So we can just say plus 0. Let's leave this term here alone, and I didn't write it back out. That term is still plus there, plus 1 over t gt. Let's just collect those terms together. So this would be plus what? gt over t times 1 minus 2 over n g sub t. Great. And let's look at our last two terms, which is minus 4. So this is negative. as long as g is non-negative, this is negative. So I can just write being less than or equal to 0 plus 0. Let's keep that last one, in fact. Minus 2 over n t epsilon squared. And I'm going to mess with you one more time. I apologize for this. I'm just going to say if the maximum is equal to n over 2. Everything still stays the same up to this point, but now I get to kill this term and call that 0. So now what we have is the whole thing is strictly negative. That was all that's actually required for this. Sorry. So if we're at a point where the maximum is exactly equal to n over 2, which is all we care about because we care if this thing goes over it or not, then our last term vanishes. But because of our little perturbation, we have an extra negative term that says the rate of change is strictly negative at this point. And that's all that matters. So then the rate of change of the maximum is strictly less than 0. So if it ever gets to n over 2, it's got to drop, which, by the way, is itself actually kind of a contradiction of ever getting to n over 2, but that doesn't really matter. So this implies that m epsilon of t is less than or equal to n over 2 for every epsilon bigger than 0 and every t. And this is a continuity thing, so we can just limit it out. And this tells us that m0, which is the maximum of f sub t of x, is always less than or equal to n over 2. Okay.
So you prove that at this particular point, the derivative of your function with respect to t goes down.
Yes.
You wanted to prove about maximum.
Right. Aha. Okay. So this is a standard estimate. Okay. This is a standard point about maximum principles. So usually what you do here is you use a forward difference quotient to actually do this. But let me cheat and just say what the moral is here. So what he's complaining about is the following. This is, I mean, even on Rn, this is a standard maximum principle point. So we want to understand this in epsilon of t, which the way we should think of this is being ddt of g epsilon sub t of xt. So we should write this as being two things, right? So this is ddt of g epsilon t of xt plus the gradient of g epsilon t times xt dot. So this is how you really want to think about it. But you're at a maximum point. So this term is 0. So that means that the rate of change of your maximum is actually going to be equal to this. And if this isn't actually varying smoothly, the point is you actually do a forward difference quotient and you still have an inequality here. I mean, that's the point of how this goes. I'm not going to do that carefully because this is, even if you did this for the heat equation on Rn, you'd have to do this. And this is sort of a standard point, so I'm going to leave it be. Okay. Oh, my Lord, I'm halfway through my first page. Well, let's use this for something before we go on. So, who cares that we have this nice inequality? What can we actually use it for? So, the corollary of the differential Harnack inequality is the standard Harnack inequality. And what it says is the following. So, again, we'll take some space, complete, say Ricci's non-negative. But again, there'll be a version of this if you have a lower bound, but you add a k to something. I mean, the errors are kt even. It's a pretty small error. And let's fix our favorite 2 points inside the space. And 2 times s less than t. Then if we look at any solution of the heat equation, I'll call it U sub r now to distinguish between s and t, I guess. Then we have the following comparison. We have that U sub s of x. So we're taking it u. We're looking at the solution at time s and evaluating at some point x. And we're saying we can compare this to our function u at time t evaluated at y. And the difference here is a quotient. So we have it's less than or equal to s over t to the n over 2 times e to the distance squared of xy over 4 t minus s. So this is called the parabolic Harnack inequality. So that's the proof. Proof is actually pretty simple once we have the differential Harnack quality. So note, let's just rewrite that since it's going to be useful. We have the gradient of the log of u sub r squared minus ddr of the log of u sub r is less than or equal to n over 2r. So let's rewrite this inequality just in terms of logs, because everything we have control over is involving logs. So when we log both sides there, what do we get? I mean, so what we're really trying to prove is that the log of u sub s of x is less than or equal to the log of u sub t of y plus some stuff. So plus n over 2 log s minus n over 2 log t plus the distance squared of xy over 4 t minus s. So this is really what we're trying to do. I should point out that, I mean, somehow, what the exponentials here all mean is the fact that this is somehow obtained this ratio. I mean, it actually does get attained by a heat kernel on Rn, right? So somehow that this is a nice sharp inequality, and we like sharp inequalities. So now how do we prove this? So this is what we're actually trying to prove. So what we do is we just let gamma from, I mean, it's going to be a curve in M, which I'm going to parameterize from S to T, because that'll be convenient. Be a minimizing geodesic from x to y. Constant speed, so that means that if it's moving distance d of x, y and time t minus s, that means, right, its rate of change is always the constant. That. Okay, so let's compute DDR of, so what's a natural thing to do here? I mean, we're trying to really look at the difference between log u sub s of x and log u sub t of y. So it makes sense then to actually look at the rate of change of the natural of log of u sub r of gamma of r. right? Because fundamental theorem of calculus says that if we integrate this from s to t, we actually get our result. So we really just kind of want to estimate this guy. If we can estimate this guy, then we just then when we integrate out, we'll actually have an estimate for the difference between the two log terms. So now what is this? Actually, so this is exactly the game we were talking about over here. So this is equal to two terms. This is ddr of log u sub r. So we have to hit this term first and then this term second of gamma of r plus the gradient of log u sub r. So it's the rate of change of this function in the direction of the tangent vector of this curve. Okay. But now we can actually use to understand this term, instead of trying to compute it out, we're just going to use our differential Harnack. The differential Harnack says that this thing is bigger than or equal to what? The gradient of the log of ur squared minus n over 2r. This term, on the other hand, well, let's estimate this much worse. Let's just sort of estimate this by saying, well, it's less than or equal to minus, the norm of the product of the norms of these two things. Okay. Well, let's use Cauchy-Schwarz now to sort of separate this out into two terms. So we can kind of guess. Let's just leave the first two terms alone for a moment. Okay, since we had this nice positive term here coming from the differential Harnack, we can kind of guess that maybe what we want to do is have it cancel off this term here. So if we're going to use a Cauchy-Schwarz, right, this is, a times b is less than or equal to 1/2 a squared plus b squared. Right, then what we're going to do is we're going to rewrite this in the following way. We're going to sort of view this thing as being times 2, and view this thing as being over 2. So I divide it by 2 here, I multiply by 2 here, so that when I do the Cauchy-Schwarz, I'll get a minus 1/2. Oops, do I want square root of 2? Make sure I do this right. I want square root of 2. Thank you. Then it'll be this squared plus this squared. So that'll be gamma dot squared over 2 plus 2 times the gradient of log u squared. Okay, but that's being picked precisely so that we can sort of kill off the positive term there. Because the positive term is sort of the one thing we don't really understand here, and we kind of want to get rid of all these gradient of log u's. So this thing here is actually precisely equal to minus n over 2r. The gradients of log u's cancel. And what's left is minus 1/4 times gamma dot squared over, gamma dot squared. But that's just minus the distance of squared between x and y over 4 times t minus s squared. But now what are we supposed to do? We're just supposed to integrate this from s to t, right? So when we integrate this from s to t, what do we get? So this is the log of u sub t of y minus the log of u sub s of x is bigger than or equal to, what is this, minus n over 2 times log t minus log s. And then this is just a constant, so we multiply it by t minus s. So minus the distance squared over xy over 4 times t minus s. And that was exactly what we were trying to prove, right? Just throw the terms on the other side. So the point is that for positive solutions of the heat equation, it's not just that the solutions of the heat equation are pointwise close together. I mean, that would follow just from a gradient estimate or something. It's that the logs of the things are pointwise close together. So in particular, if the thing is, say, very close to 0 or something, then nearby points have to be sort of correspondingly close to 0. That they can't, gradient bounds wouldn't necessarily stop them from going under 0 or way above. But this is a much stronger estimate. Okay. So I do not think there's time to prove the next statement. So we've basically gone through Harnack inequality so far. And we want to use the Harnack inequality for something. Now let me actually say what the goal is, since this is what we'll sort of get to tomorrow. The goal is to see the following. So if we have a space, and I'm going to say with non-negative Ricci, but this fully well holds if I had some sort of lower bound, but I got to add some KT terms or something like that to this, then for every epsilon bigger than 0, there exists some constant depending on n and epsilon. You can actually make this pretty explicit, but we don't really care so much, such that the following holds, such that we want to look at the heat kernel on our space. Now remember that this heat kernel is exactly going to be equal to, let's actually do the two estimates separately, because I don't think I've got enough room to write that off in the middle. If we were on Euclidean space, this would be what? I mean, up to some multiples of pi and nonsense, that this would be like t to the minus n over 2 times the e to the minus distance squared between x and y over 4t. And we want to see we're actually close to this, both from above and below. So it's at least less than or equal to our constant. Now, we want to be careful about these t terms here. So in some sense, this is what volume's all about. Well, what's the best way? I mean, if you're looking at the Gaussian measure in Euclidean space, which means that this t to the minus n over 2 term, you should be interpreting this as the volume of the ball of radius square root of t. 1 over the volume of the ball of the radius of square root of t. And it may sound funny, but the point is that t here, this is the heat equation, which means t is like distance squared, which means if you have a t, the radius that you care about is the square root of t. And it's important to interpret it this way because that's really what you want to stick here. So in fact, it's the volume of the ball of the radius of the square root of t of x minus 1/2, because we'll have a y as well, times, I don't even have enough room to, volume of the ball, square root of t, y, to minus 1/2, times the exponential of the distance squared over xy over 4 times, now you got to lose a little bit in the Gaussian. That's the key point. So it's 1, what's worse, minus epsilon or plus epsilon. We want the constant to be a little bit less up here, which means a little bit more down here. T. So up to whatever our multiple here is, and up to the epsilon here, this is sort of exactly what the behavior in Euclidean space is. And it's saying on a space with lower Ricci, we have the same behavior. This is 1. And the second thing we'll show tomorrow is just the converse. In fact, the converse implication just follows from the Harnack inequality. So once you have the upper bound, you can actually prove a lower bound without too much extra trouble. So that is rho sub t of xy is bounded from below a C inverse times the volume of the ball of radius square root of t of x minus 1/2 volume of the ball of radius square root of t of y minus 1/2 times e to the minus distance squared of xy over 4 times 1 minus epsilon t. Okay, so that is simply to say that heat kernels look like this. I mean, they look the way you expect them to look in your space. So, I mean, this is nice and this is interesting, but this is actually incredibly powerful. We're gonna use this to build things like smooth cutoff functions with Laplacian bounds and stuff like that, and that's going to be the key point. I mean, where I would have liked to have gone if we had, say, an extra day, is that the first key thing you want to see in spaces with lower Ricci bounds is that if you have a harmonic function, then in fact the Hessian is automatically in L2. So that is, you have uniform bounds in L2 for the Hessian. You do not have bounds for 2 plus epsilon. I mean, so your Hessian's in L2. It is not in L2 plus epsilon. And if you could prove that, there are actually a huge number of conjectures you could prove, but I mean, it's wrong. I mean, it simply isn't true. And a key point of proving that is going to be to construct a nice cutoff function that we can use, and this is going to be the first step toward that. So anyway, we'll tomorrow pick it up and use the Harnack to prove this. Okay.